All right, everybody. Good night again. If you just caught me yesterday, I was looking at Microsoft's new CNTK deep learning library and was able to get it to do something eventually using an old compiled binary. But tonight, we're back to usual with Theano, and we'll actually be looking at something that I'm still getting my head wrapped around, convolutional neural networks. And so at deeplearning.net, where they also have the Theano software and tutorials, they have a pretty good tutorial on CNNs. Although it sounds weird to refer to it as a CNN, so I might just say convolutional neural net or convnet or other things like that. So let's look at this page. We're at deeplearning.net/tutorial/Linnet. If this gets too complicated, there's other sort of bare bones things on GitHub where people walk through convolutional neural net. So in about 100 lines, they get something simple down. So that's pretty nice. And there's other ones. If you search for them, you'll find them really quick. Not hard at all. All right, so you might recall we had a multilayer perceptron last week. Not really a perceptron, but a multilayer neural network that makes it deep if you have like a hidden layer and more than just input and output. So you can keep building those layers, and we did that, you might recall. We had a variety of layers. In fact, tab new MyMLP. Yes, we had something like this. We had test MyMLP. Let's go find that top line. And we said, hey, how many layers do we have? Do we even have that here? Maybe we don't. Maybe I lied. I'm a horrible person. I'm a horrible person. All right, well, we did actually do that. We had multiple hidden layers in our model. And as you get more and more layers, you get more and more parameters. And so you need a lot of data to train it, and you constantly risk overtraining. And you start to wonder, do I really need to connect every neuron of this layer with every neuron of the next layer? Do I need to wait for every single one of those? That's going to get really big really quick. So convolutional neural networks are sort of a way to say, well, we don't need to connect every neuron. You don't need a fully connected layer. You can have sort of a sparsely connected layer. And you might just say, well, how do I decide what neurons to connect to what? If you have something like an image, you can do this in sort of the obvious way. You say, well, pixels that are near each other, those things should feed into the same feature. And that's sort of exactly what we're going to do with a convolutional neural network. You can take your image, instead of having 728 or 784, whatever distinct feature, 28 times 28, 784 distinct features. You can write those in a 28 by 28 matrix or array, however you want to think about it. And those pixels that are near each other, you're going to have those all feeding into equivalent neurons. You're going to feed them in and do something cool on them and get something local out. And in particular for an image, you might say, well, I'm looking for the same kinds of things anywhere in an image. Maybe you're looking for a dog somewhere in the image. You don't care where, so you're going to probably end up having the same weights on each little box of the image. You're just going to be moving this box around. So it'll save you even more parameters. And there's lots of other things. Anyway, let's just kind of start walking through this tutorial. As said before, this assumes that we did the classifying digits with logistic regression, which we did, and doing the multilayer perceptron, which we did. And it assumes you did some basic stuff, which we also did. Dim shuffle I didn't look at, but that's okay. Conv duty also did not look at that. But again, that's all right. Figured out. GPU, we have the GPU working, which is good. And apparently we're going to be looking at the Three Wolf Moon image. If you're not familiar with it, it's this one. It's a very popular t-shirt that blew up on the internet several years ago. You can probably get it at your favorite online retailer. And they have some code available. We're going to try to be programming our own, but we'll use theirs as needed. So the catch here is that CNNs are sort of biologically inspired by actual like cat visual cortexes, excuse me. So there's the idea that animals actually see this way. Let's look at what they say here. Cat's visual cortex. Visual cortex contains complex range of cells. sensitive to small subregions of the visual field. So that's the key. Some neurons are only activated by certain areas of the visual field. They call this the receptive field. Additionally, 2 basic cell types have been identified. Simple cells respond maximally to specific edge-like patterns, and complex cells have larger receptive fields that are locally invariant. I don't see how that's... Alright, that's interesting. We'll get to that later. So that's just kind of where does this idea actually come from? Well, we studied animals. We said, hey, they view things this way. There's a good chance humans do in a similar manner. I don't know. I'm not a biologist. I haven't studied anatomy to any great degree. So the catch is, not the catch, the great thing, this is sparse connectivity. So rather than every single neuron feeding into every neuron of the next layer, some neurons feed into some neurons of the next layer, some feed into others, and that's okay. You don't need a full activation. You just want to connect the neurons that are sort of intelligently connected. All right, and here they're saying m-1 is the input retina. So these are like sort of the pixel values on the bottom layer. Receptive field. Units in layer M have receptive fields of width 3 in the input retina. Oh, so here, yeah. If this is, imagine if you can only view things in a one-dimensional world, so you can only look at things on a line, and so each neuron can only point to its nearest three neurons of the next layer. So your receptors, you say, well, this pixel value gets sent to this one, this neuron, and this neuron. This one gets sent to this neuron, this neuron. There's no other neuron over here on the left. Otherwise, it would get sent there too. So we're making use of the structure of our input data, that it's actually coming in as this is a line of input. If you just have sort of arbitrary data without this structure, this might not make sense to do on your data. So for things like images, this is perfect because you've got a very two-dimensional structure. And if it's a color image, you probably have a three-dimensional structure because each color channel might be used separately. Because something might look like grass or it might look like dead grass or something like that. All right. We see the receptive field, and here they're saying the receptive field is of width 3, right? Because the neuron connects to 3 things at most. And note that in this case, if there's no neuron for it to connect to in the second layer, like this guy only has one guy, they're just saying, we're not connecting to anything else then. So we're gonna talk about padding, which will sort of determine how we deal with the edge cases. We say the receptive field with respect to the layer below is also 3, but the receptive field ensures that learned filters produce the strongest. Each way, hang on, I skipped a line. The receptive field with respect to the input is larger, 5. The receptive field with respect to the input is larger. Okay, interesting. Each unit is unresponsive to variations outside of its receptive field with respect to the retina. Maybe because these 3 consume 5 neurons? I don't know. We'll get to that. Stacking many layers leads to nonlinear filters that increasingly become global. So your information slowly feeds around. It takes a while for one pixel to affect everything, but it will eventually, and that often makes sense. Shared weights. In addition, CNNs, each filter HI. So a filter, I don't know if they explain it that much here. Your filter is sort of a feature you're going to compute on a set of on a small subregion of your image, say. I had to sketch out this big thing when I was trying to make myself understand how this applied to the digit classification. So let me just try to explain that while we're ignoring this. That'll be good. You've got your 28 by 28 image. Actually, I was going to do something cool. I was going to open up GIMP. GIMP's a photo editing program, or just general goofing around drawing program, which is fine. New is fine. Yeah, whatever. That's good. Whoop. I want something not nearly that large. Okay. Oh, jeez. Really? Hang on. I want the pencil. There we go. Pixel size 1. There we go. Okay. So if you've got your 28 by 28 image over here, yada, 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 yada. How's that look on screen? We'll find out in a second. I don't have an actual Wacom tablet. Oh my gosh, that's awful. So that's 28 by 28. You want to look at a small subregion of the image. Maybe there. And what you're going to do with that is, hang on, I gotta pause for a second. Look at my stupid notes. I actually made notes this time. Not that I'm cheating. I'm not cheating. I just don't want you to look at me more saying, oh, what is he doing? Not doing anything. Okay. So let's say we take a 5 by 5 slice of this. I know this image only looks like it's 5 by 5, but that's fine. We're going to pretend that's our little miniature neural net. That's what's feeding into the next layer. We're going to compute features on this 5 by 5 layer. Each feature is sort of like another neuron in the next layer. So our inputs are the pixel values. And we might say, well, I want 32 neurons on the next layer that this little 5 by 5 block will feed into. And so I'll need a weight from each little 5 by 5 guy here. But only in this part of the image. I'm ignoring the other parts of the image. And so what you can do is you can take this 5 by 5 block, compute 32 features for it, and then you slide the block over. And how you slide the block over is sort of called your stride. You can either say, well, I don't want my regions to overlap at all, so I'll slide it over 5. And so then you'd have a new region. Maybe this is your next region then. And that's one thing you need to do. Or you might say, you know what? I do want things to overlap. And maybe you have a stride of 1. And so you're doing this. There you go. Look at that. Beautiful. Beautiful. And so you just slid it over 1, and now you're computing features on that. So it's like you've got your input neurons, or all whatever these guys are. And imagine these are your 5 by 5 neurons. And then I'm actually gonna increase this. Then you're gonna have all your features over here. And you're gonna connect all these guys. Also, I mentioned you might have multiple channels. So you might have 32 sets. You got 32 times however many channels you got. If it's a black and white image, you only have one channel. But if you've also got like red, green, blue, you're going to have ones for that too. Bum, bum, bum. Let's suppose you had 2 colors for whatever reason. You know what? No, that's silly. 3 colors makes more sense. Let's go green. Bang, bang, bang. We'll sneak that one in there, put that one over there. It doesn't have to be exact for just drawing purposes. And of course, you're connecting all this to all this. Each one of these connects to all these guys. Yada, 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 dot, dot, dot. So that's fine. So you do this on a particular 5 by 5 block, and then you slide it over, and you do it again. You slide it over, and you do it again. You slide it over, you do it again. When you get to the end, like the last 5 by 5 block where it's full, you sort of have an option of, well, I can do a 5 by 4 block and I can lose a column, and what do you do with that extra column? And so that's what's called a padding. So you can fill it up with zeros, you can like copy some other stuff. It might depend on the structure of your data. Like if you imagine you didn't have a square image, but it was wrapped around a cylinder, that means like the first column of your image would actually wrap around to the second column of your image. For an image, that doesn't really make sense. But if you were looking at something like a globe, then you have this kind of nature. And so then it'd be sort of obvious what to do. Is, oh, well, yes, well, this copies back around. And you go all the way around. Like I said, that depends. All right, so let's come back to that. So each filter, wherever they say filter, you can sort of mentally replace that with, that's another neuron in the convolutional layer. Or that's another feature that we're pulling off that 5 by 5 block sub-image that we've got. Each filter is replicated across the entire visual. At least that's how I've seen it used in other tutorials. If this one talks about it differently, we'll see. These replicated units share the same parameterization. So this is shared weights. So you might imagine if you got this 5x5 block, you're looking for some features in it, and suppose, like I said, you're looking for a dog in the image, and you've got your network trained so that within this 5x5 block, you will hopefully find a dog. Well, the features to find a dog should be the same no matter where in the image the dog is, right? So that's where you use the concept of shared weights. If you got all these 5x5 blocks, they're all producing all these different features. Shared weight says, give them all the same weights. So you're still computing like unique features because you've got different inputs depending on which 5x5 block you're in, but you're using the same weights. So if you did have, for instance, identical parts of your image, maybe there's 2 dogs in it, they should give you the same output to whatever the next layer is. So the same weights, the same bias vectors. This also means you have fewer parameters to worry about. Instead of having a parameter for every single block, you only need one for the blocks for all the features. And again, this only makes sense in that case where you have an image and you don't care where it occurs in the image. If you use something like a convolutional neural net to try to help you solve the digit classification problem, we know the digits have been centered and put like face up or right side up in the image. So that's not necessarily going to help to share the weights if you did something like that. Anyway, let's keep going. We haven't talked about the pooling yet, which maybe we'll get to that later in this. But that's what shared weights is. And so here, like the same colors, that's what these same weights are. So that's a little bit easier to see right there. So the reds are all, that's one weight we're computing. The blues is another weight, and the greens is the third weight. And it's sort of like where that object is, or where that neuron is in the 5x5 block is kind of helping determine that. Okay, replicating units this way allows for features to be detected regardless of their position in the visual field. Like I said, doesn't matter what block it's in. So that's nice. Okay, details. So this is kind of things that maybe I glossed over or they glossed over, and then they say, oh, how do you actually do this? A feature map is obtained by repeated application of a function across subregions of the entire image. What the hell does that mean? That just means we're going to cut up that 5x5 part of our image or whatever, and we have some out, and that's going to feed into a subset of neurons on the next layer. This is called a convolution because doing this operation on the 5x5 block, you do it on this part, and then you move up and do it on the next block, and then the next block. That's why it's convolving this little function on a larger set of your image. So don't worry about it being called a convolution. You're picking a block, and you're computing your 32 or whatever features on the block. Then you move the block, and you compute the features again. And then you move the block, and you compute the features again. And for a given block, it only ties into its features in the next layer. But each block has its own set of features that it ties into, even if the weights are the same. Note that it's going into different components here. Okay. And also, if you have different channels, like the red, green, and blue being your different channels, that adds another third dimension in your problem space. So you got weights for every feature. That's what they're showing here. The different colors are sort of the different features we're working with. That's what this third dimension comes from. Just like imagine each box is like the image, so each pixel is like an input neuron. And you see they've got the little sub-image there, a little 2x2 thing. That goes into to the next layer. We're not going to worry about the explicit computations. Here they're using hyperbolic tangent sort of as their activation function. That's fine. Whatever's convenient. It has some nice features. I'm not going to talk about those. For rich representation, each hidden layer is composed of multiple feature maps. Yes. because you might want to find multiple things in your image, right? And it's not even that like, oh, this is going to find a dog. Your first initial layer features are probably finding things like edges, or maybe like this is vaguely a circular shape or something like that. This figure shows 2 layers of the convolutional neural nets. Yeah, so this is like our input. This is the convolution, or the convolution. What you're sending it to. I guess you're convolving here. Putting it all together. WIJKL denotes the weight of connecting each pixel on the kth feature map. Remember, we're doing lots of features on our 5x5 sub-image block at layer M. M being like what channel we're on. No, sorry. M is what layer of the neural net we're on. So like if you're at the first one, you would say 0 or 1, depending if you're a computer scientist or mathematician. With the pixel coordinates ij of the, is this the elf? Is that what this is? Yeah. One of those things about Roman letters, man. L and I and O and 0. Get burned by that all the time. All right, of the elf feature map layer. So you can have multiple features of our... In fact, you often do want to have multiple features in your 5x5 block. And so you got weights for each of those features. The convolution operator, convop. So here's what we're learning. Main workhorse for implementing convolutional layer. And I promise we will get to actual coding and maybe do some nice things. Convop is used by Theano.tensor.signal.conv2d. Takes 2 symbolic inputs. A 4-dimensional tensor. Get used to seeing these 4D tensors a lot. They come up in this. Corresponding to a mini batch. Remember, the mini batch is how many images we're training on at once, because we can use our current status of the net, compute them, send the mini batch through, see how many we got wrong, and then update all the weights. It's a little faster than doing after every image, and still gets us some benefit, as opposed to running through the entire data set and then doing it. So how big is the mini batch? What are the number of the input feature maps? So how many input pixels are we doing, I think. The image height and the image width. So it's specifically for a 2D kind of thing here. 40 tensor corresponding to weight matrix W. Shape of this tensor is number of feature maps at layer M. So that's, what is that, K or L? L? What is K? K is the kth feature map at layer M. The lth feature map at layer M minus 1. That's M minus 1, that's layer M. So this one has K, this one has L. This one has 4, and this one has 2 on the next layer. Confusing, man. Real confusing. Number of feature maps at layer M, number of feature maps at layer... So the number of neurons at the next layer, or at the current layer, number of neurons at the previous layer, filter height, and filter width. This should be how many features we're computing on our small subblock. I feel like they might be using filter differently than I'm used to, or maybe I have a misunderstanding of filter. We'll get to that. Input consists of 3 feature maps, RGB color, that's right, because we're looking at Linnet, I believe. And we're going to use 2 convolution filters with 9x9 receptive fields. So the image is 120 by 160, so it's not square. Oh well. 9x9 receptive fields, so instead of 5x5, we're looking at 9x9 subblocks of the image at a time. So we're going to be dragging that around. What do they do here? They just set the random variable. They use the input keyword again, which is terrible. W shared P. So 2, 3, 9, 9. What's the 2 here? Because there's two filters. They're computing 2 features on their 9x9 field. So they're going to have 2 of those neurons, but they've got 3 They've got 3 channels. Because they have red, green, and blue. 3 colors to work with. And something might be interesting in red, and it might be interesting in blue, but it might have nothing in green. Just the way it goes. So they're going to initialize all these. Theano.shared. W bound, which I guess is however many pixels you have, or like input neurons times however many channels. Oh, so that's like the total number of input neurons is this 3 times 9 times 9. Because we've got 9 by 9, 81 input pixels times 3 channels. So 243, that should be, if I can do my math right. They RNG.uniform, they set some uniform, set some of this stuff. They initialize it to just some random stuff, and that's W. How big is this? W bound? 1 divided by W. Oh, right, it's derp to derp. They divide by W bound, so it's between a very small number and a very large number. So it's sort of equally spread out the probability. Okay. They do the same thing for their bias vectors. Initialize certain important. Biases are usually initialized to 0. In this particular application, we simply apply the convolutional layer to an image without learning the parameters. We therefore initialize them to random variables to simulate learning. Oh, so in this particular little sub-example, they're just initializing random crap to their weights and biases, and then they're going to see what pops out, just to show you what the convolution does. You know what? Let's actually just run this. Let's do that. But let's not run GIMP right now. Oh, man. Let me squash GIMP out of the way here. Perfect. Except let me... There we go. Oh, no, something bad happened. Module Theano has no attribute tensor. What's going on here, buddy? Import Theano. How does Theano have no attribute tensor? Oh, did I not? No, I did that right. If my Theano is broken, like, I don't know what the hell I'm gonna do. Okay, that's fine. From Theano import tensor is T. Naturally, things have to break, of course. You know what? Theano.tensor? Theano.tensor is right there, buddy. Import Theano.tensor as T. Right? Yeah, that's totally fine. I don't know why they had some problems with my... Alright, I'm going to kill... The GIMP's just getting in my way right now. Discard changes. There we go. Let's try auto indent. Maybe that was my problem. There we go. Much better. Make some random variables. And here's the catch. Here's where we're going to do some convolving. Input, recall, is all the input pixels. T.tensor4 name input. And we never actually assigned it to anything. Oh, but we're just describing the graph. We do con2v with input and W. Build symbolic expression that computes the convolution of input with filters in W. So there we go. What is dim shuffle? It's a powerful tool in reshaping a tensor. What it allows you to do is shuffle dimension around, but also insert new ones, along which the tensor will be broadcastable. Oh, so it's like numpy.reshape. Dim shuffle x2, x comma 0. It doesn't say what it actually does there. Work on 3D tensors with no broadcastable dimensions. The first dimension will be broadcastable, then we'll have the third dimension of the input tensor as the second. Make a 0D scalar into a 1D vector. Cool. Turn the identity, inverts the first and second dimensions, so put the 1 in the first position, the 0 in the second. Well, it's like taking a transpose, I guess. That's kind of cool. Make a row out of a 1D vector, so n to 1 by n, that makes sense. Make a column out of a 1D vector, n to n by 1, sure. You do a times b times c to c times a times b. It's just like reordering things. So that's what they're doing. Oh, geez. So what is this doing? You know what? Let's look at dim shuffle. Let's get the details of dim shuffle here. Thought we looked at this, maybe not. Dim shuffle. This is not additional information, unfortunately. Turns a view of this tensor with permuted dimensions. Make a row out of 1D vector. Make a column out of a 1D vector. A times 1 to a times b to a times 1 times b. So x inserts a new dimension. So in that case, what are we doing? We're saying b, our bias is, we're turning b into a 4-dimensional vector, into a 4-dimensional tensor, excuse me. We're putting the actual b dimension on this second axis, and we've got these other sort of dummy axes that are all going to be times 1, I suspect. Unless we haven't defined x anywhere. So yeah, that's all it does. So that's interesting. And that's to make it work nice with the convolutional output. That's all. And then they compute the function. Copy. Do. So we're compiling that now. And they say, let's have a little fun. All right, sure. Doc images. I don't know that I actually have that. Cpodge Theano. Let me remove this old that garbage. How do I would like to download the image. Oh, well, the 3 Wolf Moon image. Let me go ahead and download that. There we go. So we're actually going to do some cool visualizations. We're going to look at different channels of the image here. Let me grab this stuff. Grab that, actually. Note I'm not actually like doing any coding over here just yet, but that's okay. img equals image dot open. Yeah. Open. It's going to be 3 wolf moon dot jpeg. Nothing fancy there. I can't decode whatever. Read binary. There we go. One of those things, man. Python 3 and Python 2. There's a chance this is going to burn me too. We'll find out. Alright, there we go. So that is reading in the image, just like that. So we say image.shape. Again, that's numpy. Just telling us how big the image is. 639 by 516 by 3 for red, green, and blue. Again, 3 wolf moon. Numpy.asArray, we did that. Image underscore, we're going to transpose the image to turn it into the right vector shape. So we still have 3 channels, and we still have our height and our width right here. And we have one sort of dummy channel, or dummy dimension right here. Let's do that. This is going to look cool. Don't worry. And ours is going to look slightly different, but that's okay. Plot the original image and the first and second components of the output, right? No problem. Subplot 13x. Where did we actually run our... Oh, we called f. That's where we ran our function. Our randomly trained convolutional neural net. Pylab.show. There we go. That was unfortunate. That should have showed us a little bit more. Oh, here we go. Filtered image is not defined. Why not? Did I not actually compute filtered image? If I didn't, I'm a horrible person. Filtered image? Did I not just like actually... Why didn't that actually work? Hey, buddy. That's super weird. Okay, now it's there. Now it's something. That should have been like... That should have assigned. There's no reason it should not have assigned. Am my output not get computed? No? My output's normal? That's weird. Might be a Python 3 versus Python 2 thing. And hang on. Python crashed. Wonderful. Wonderful. Let's try this one more time. This is just to show you what the convolution is doing. It's pulling out different features from the network. This is all. But it's a cool visualization, so I'd like to have that working. That would be a good thing. Okay, that compiled very quickly this time. Imagine that. And this is IMG equals 3 wolf moon IB. So IMG is a regular thing here. It's got actual dimensions. It's RGB. Should be able to do this just fine. There we go. Let's try this then again. Yeah, that's super duper strange. I don't know why the hell. Bad input argument. Cannot store a value of D-type float 64 without risking loss of precision. If you do not mind this loss, you can 1 explicitly cast your data at float 32. So that's probably what I should have done. So that should probably be D-type float 64 or float 62, float 32. Ugh. So let's do that instead. And then let's run this again. See what happens. Hey, what do you know? Filter to IMG. Hey, that's our actual array. That actually worked. Beautiful. Now we're going to show everything. Bing. Our original image did not actually plot correctly. That's amusing. But we did extract these two other images, which is kind of cool. And if we look, filtered image 0, 0, everything, everything. So that's this channel versus the next channel. There's actually a mini batch of size 1 here, so we take index 0 in the first dimension. Oh, that's what our mini batch size is, so grab the first image. And our second dimension here is which channel we're on, so red, green, or blue. So we ought to be able to look at all these. I don't know why that first image didn't actually work. That was kind of weird. But that doesn't matter. So let's look at 0, 1, and 2. I want to see what the other. Index 2 is out of bounds. I thought it was red, green, blue. Is it not red, green, blue? Is that not what we're looking at? Size, it's just shape 3 here. I must be misunderstanding something. Filtered image, subplots, 1, 3, 2, 1, 3, 3. I thought it was 3 for the 3 channels I was working on. Zero. That's a little weird. That's perplexing to me. That is a problem I'll solve on another time. But not right now. The point being, we extracted different features from different channels. And we're using this convolutional operator to look at small sub-areas. Are we looking at small sub-areas? You know, I'm not even sure anymore. Not with this particular. Yes, we're looking at 9x9 regions. That's right. Ugh, what a mess. All right, so you can pull out various regions, little sub-regions, and call your functions on them and pull out these interesting things. And in this case, it kind of looks like an edge detector. And that's just with random weights, so that's kind of cool. All right. So that's sort of like the first part of convolutional neural networks. You build up these little n by n boxes, and you've got some features that you're computing on all of them. If, however, but you might say, well, we've got a whole bunch of features on this, but like, are all the features really important? And so that's when you get to like max pooling. So we're going to add another layer after we do this convolution. So now we've got a whole bunch of features computed for every little box, even if we use the same weights for each box. We'll have different values of inputs, different pixel values. And you'll want to say, all right, well, we don't need all that garbage. Most of it is probably not interesting. We only want the best one, or we want the sort of average feature. Like if you're looking for a dog, or if you're looking for an animal, and your feature, this is just an abstract example. If you're looking for an animal, and your features are like different animals that you can find, and most of them are like, well, it's probably not a donkey, it's probably not a cat, it's probably a dog, it's, you know, sort of maybe a hyena. You really only want the one that says it's probably a dog. Everything else is just sort of a wash. It doesn't really help you to hang on to that information. So that's where we're going to get into max pooling. So max pooling partitions the input image to a set of non-overlapping rectangles. One more catch, sorry. Let me rewind a little bit. You've got these 5x5 blocks or whatever, and maybe they're overlapping and maybe they're not. So you say, all right, I take all those. In each one of those also can like form another, those have a natural order in an image, starting at the first 5x5 block and heading on over. You can say, well, what does this 5x5 block compare to the one right next to it? And the one below it, and the one sort of catty corner to it, or kitty corner, or that reveals a lot, apparently, about where you live. If it's kitty corner or catty corner, or if it even exists at all. Total aside. You do that. You've got these 4 5x5 blocks, say, and you say, well, I really only want the most important, the biggest value from each feature of these 4 adjacent blocks. So that's what's called max pooling. So you're sort of looking at a larger section of the image, but you're looking at only those features that you pulled out before. And the most common thing that I've seen is max pooling, where you say, all right, pull out the most important, or say, suppose you had one feature. So you've got one feature for each of these 5x5 blocks. So you've got like one number in this little you've got 4 numbers in this 2x2 array, one for each of your blocks. This is why I had to draw so many pictures. I went crazy trying to sort this out. So you compute those 4 different numbers. Max pooling says, just take the biggest one, and that's what you're going to have. And you're going to pass that into another layer of your neural net. So again, you're throwing out information that you don't really want. Because like this layer says, hey, I think I found a dog in this section. So you say, aha, a dog. And you don't care that you sort of found a cat, or meh, that in this other section you maybe found a banana, whatever. Okay, and then you talk about it's useful for vision for 2 reasons. You eliminate non-maximum values, less things you have to compute. Provides a form of translation invariance. That means that if something is in a certain position in your image, or it's slightly shifted, doesn't matter. Your model will be kind of robust to that. If max pooling is done over a 2x2 region, 3 out of the 8 possible configurations will produce exactly the same output of the convolutional layer. Nice. For max pooling over a 3x3 window, it jumps to 5 out of 8. Nice. So I see 2x2 being the most common, but 3x3 could work as well. And again, this is how many of those 5x5 blocks, or 9x9, or whatever sub-blocks of the image that you're looking at. And how do you actually do this in Theano? Theano.tensor.single.downsample.maxpool2D, of course. I mean, that's totally the natural thing to do. So like the tensor is operations that work on tensors. Signal, the real reason that this is in signal is here is because it's using this downsample operator. Downsample just means I've got maybe like 100 observations. I need to cut that down to 10. I need to cut down the number of samples. You can also upsample, where you can say, well, I need to sort of interpolate between all these points and increase or come up with more samples. So this is where downsampling. And how are we downsampling? Max pool 2D. And so this will say, all right, for this adjacent block of my 5x5 blocks, we'll do this, or my 3x3 group of blocks. Again, this is why it's hard to like keep straight in your head. There's multiple layers of this going on. If it was just convolution, this would all be much simpler to understand. But that doesn't work quite as well. An example is worth 1,000 words. Indeed it is, my friend. So what do we got going on? We're importing downsample. That's just this thing. We've got our input 4-dimensional tensor, as usual, for this kind of convolutional thing. We're doing just 2x2 blocks, so just whatever is adjacent to my block. Okay? And again, this was some 5x5 block. This is some other 5x5 block. They might have actually mostly overlapped. Important note, when you're doing the convolution though, you never say, okay, I'll take this 2x2 block and then this 2x2 block. No, you only use each one once, because otherwise, if something's really maximized, it will sort of just duplicate in the nearby blocks, and you don't want that. I'm pretty sure that's the reason. I could be totally wrong. If I am, someone on the internet will tell me. No doubt of that. So we got our max pole shape, 2x2, very common. Pool output, so we do the downsample.maxPool2D. We slap in whatever our input is, so whatever's coming from the previous layer, the convolutional layer in this case, whatever our shape is, and ignore border. I don't know what that's going to be. I'm not going to worry about that. Oh, they're showing you how it varies. Cool. And then they compute, they compile their function. They make a random tensor, and then they compute the pool out. So this is the input values, those are the output values. They do it again with ignore border false. Let's just do that. I'm not going to run their code. I'm going to, of course, do it myself. We're compiling, and there's problems because Python 3, so we're going to look at their code. Like, oh man, I don't even like the way Python 2 does print statements. I much prefer having it as like a function, because everything else is a function, and I just want to think about things as being functions. Less syntax I have to remember. Anyway, let's go look at this. So when you have the border set to true, so we're going to learn what the border true being true means, which is good. Ignore border set to true. Da, 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 da. This is our input random values. And our output is, we're doing this max 2x2. Oh, so take the 2x2 of these guys, compute the maximum. What's the biggest one? It says 7.2, which is 0.72 really. Boom. Find the next 2x2 block over here. What do we got? We've got a 3.9 right here. So the next 2x2 block, 3.9. What happens in the next 2x2 block? We don't have another 2x2 block. So ignore border, true, says, forget it, go down to the next thing. And we look at these four here. Got a 6.8, 6.7, 6.8 I think wins. Boom, 6.8, look at that. You do the same thing. So ignore border says, if your image doesn't divide evenly, forget it. Just throw those ones on the outside out. They don't get a say. If you have to ignore border equals false, what are we doing here? So 0.019, 0.67, 0.57, these four things right here should be 0.67, great. We step over by 2, and then we look at these four. We don't want to overlap, remember, because these are the output of some convolution that we've already done. So this is going to be 0.58. And then we say these two, and you would put like zeros here. And so 6.9. Boom. Then you go on the next two rows, that's grand. And then you'd go on to the last row, and you'd sort of have a dummy row of zeros at the bottom. So 9013, it's 90. 1387, it's 87. And 39 and a bunch of zeros is 39. So that's what the pooling does. Now the full model of Lynette. That just sounds cool. It sounds very, it's like I'm saying, it's like a French woman's name. It's Lynette. And that's kind of cool. Anyway, I'm getting totally confused. So what kind of neural net is, let's increase the size of this image with my hover zoom. Actually, let's not do that. So first you've got the input image. Are these very grainy? Are these grayscale? Looks like maybe they are. You do this convolution. You compute 4 features on every little subblock that you've got. So you've got this n by n subblock here. You computing 4 different features on it. So you've got a weight for every pixel in there. And probably you've got the same weights for every for every different block. Compute those 4 features. On each feature, you're doing, they call it a subsampling. I feel like they really mean pooling. Maybe that's probably just another way of saying pooling. So you take on a 2x2 block in there. You say, what's the biggest activation in this feature of these nearby blocks? Boom, that goes into this. You still have 4 feature maps, and now you've got a new block size. So if the input image is, let's just say for example, if it was 28 by 28, like a digit, and you looked at 5 by 5 blocks, and let's say that you only looked at blocks that were fully inside the image. So if you looked at a block that was only partially in the image, you say, nah, throw that out. Then you would end up with your full 28 minus 5 plus 1. You'd have a 24 by 24 set of blocks, because you're going to have 24 blocks going this way and 24 blocks going this way. And if you computed that many features on them, well, you'd have 24 by 24 times 4 features, or 24 by 24 times 24 times 4 sort of like neurons on that layer. But they're not all heavily connected, so it's okay. And then on each of those, on each 2x2 block of those blocks, you're going to do your max pooling. So I take the first block and then the next block. Let me bust open GIMP again. People, I saw a comment that someone was really enjoying the drawing. Well, let me see if I have Color Paint installed. I don't. Okay, GIMP it is. New file. Yes, totally new file. That's what we're all about. That's great. So just to kind of, I really don't want. No, that's not what I wanted at all. That is not what I wanted. There we go. So you got a block here and a block here. These are all your 5 by 5 blocks or whatever. And you decide which one of these for a given feature is the biggest value. And then you say, all right, that's great. We're going to pick one of them. That's green. That's the one we're choosing. These other values, they're gone. And you do this for every block, or every 2x2 group of blocks that are not overlapping. Right? Not overlapping. And maybe different areas have different regions are more important in other places here. Got select all, none. All fine. I don't care. I don't care. All right. Well, that's the idea anyway. And so you're losing like 3 for every 2 that you're doing. So you're cutting your data by 3/4, which is nice when you do the pooling. And you only grab sort of like what you think are the most important ones. We'll discard the changes. We don't care. All right, and then you do this again. Once you've done your max pooling, you do another convolution. So you say, well, what are these things that are next to each other? Get some features on those, and then you do another subsampling or max pooling. And then it's often you do a fully connected layer. So this feeds into whatever the rest of your deep learning network is. And then that feeds into your classifier finally. All right, putting it all together. Let's just take a look instead of coding our own thing here. It's not about the programming. And my Python crashed again. I'm telling you, this is terrible. But we are gonna have to, of course, do a couple things. Can I do 2 to 3 real quick? 2 to 3 and 2 to 3. 2 to 3. Did I use this before? All right. Hang on. I got to remember how to use Python 2 to 3 to just fix this for me automatically. Python 2 to 3. example. Automated Python 2 to 3 code translation. I don't want the diff, I just want the new. Diff against the original force. Writing the changes back is enabled with the W flag. Okay, that's what I want. So I want to fix this. Files are modified. Fantastic. I'm going to be bold and I will run this without even looking at it and we'll see what horrible things happen to me. Look at that. So here they're using their previously built up logistic regression and hidden layer models, and we'll see if my change to hidden layer totally borks everything. And if it does, that's okay. It happens. So what are we doing here? Right, so this is having a convolution and pooling layer. Often, this is a pool layer of a convolutional network? Interesting. Oh, Linnet conv pool layer? Is there like a Linnet conv layer? No. So I'm managing, they combine their convolution and their pooling. That's often done. This might actually take a while, so maybe this wasn't a good idea. A good thing to run in that case. Is this a quick example? Is this like MNIST stuff? This is with a random data set. What about this one? We're almost out of time, but that's okay. And I know we haven't gone through the actual programming aspect to it. But that's not something that I want to spend as much time on just right now. Cross entropy, yada yada yada. Here's the dim shuffle that we saw. This one also has momentum, which is just a training thing that's slightly different. What data set is this using? Sci-Far 10. Okay, that's interesting. This one, however, is using random streams. Categorical cross entropy. So Sci-Far 10 is a classifying color images into, like, I think one of 10 categories, like a dog or an airplane or this, that, or the other thing. MNIST. All right, so maybe this one is doing the responsible thing. Float object cannot be interpreted as an editor. So that almost worked. That almost worked. Story of our life, huh? All right. So paste. Let's try this thing, shall we? So this is a slightly fancier convolutional neural net model. For example, instead of this hyperbolic tangent, we're going to use something called rectify linear. That's a different kind of activation function from like the sigmoid. Basically, it's itself if it's greater than 0, and if it's less than 0, it's just 0. So it's a way to sort of turn a neuron off if it's not giving you a strong activation. But if it is giving you a big activation, then you're very interested, and you still are keeping track of the scale of that activation. So that's not really a big deal. And you might notice, like, that's kind of popular here when we're doing the max pooling, because you're doing this max pooling, but what if something's really negative? Maybe that's important to you. Like in the sigmoid, that can still, I guess in sigmoid, that doesn't actually affect things. I'm thinking if your activation were still, that would give you pretty much 0. All right, so maybe it's not a big deal. All right, we're running CNN. We're saving this. CNN.py. Invalid syntax. Breaking my balls here. 2 to 3 people, Python 2. Files that were modified. Okay, let's try this again. Even if this doesn't work, that's okay. New module name load. From load. Import MNIST. I don't know what that's about. Let's see if we can do that. He's got his own load function. Yeah, he does. It's one of those things that load.py. Oh no. set paste. When you paste into Vim, gotta make sure you set paste there. There we go. This is the standard digit classification training set that we've been working with before. Else, oh, really? Didn't know really. Okay. No such file or directory. Well, of course there's no such file or directory. Why would I have it plugged in? Datasets dir. No, that's not where it lives, buddy. That's not where it lives. All right. Turns out we are not going to screw around with that right now. Maybe we'll come back next week and actually run more of these networks. But I think we did some good stuff of going through what the heck a convolutional neural net is. Hopefully we'll spend more time on that in the future. It is kind of a bummer that neither of these things directly worked. And they always depend on hard-coded things as opposed to like downloading it from the net. All right, but that's a convolutional neural network explained at least. And you can work through this and get the code, and you can see what kind of things happen. And here they just show you, oh, it ran. Look at this. You get a very good scoring rate with these without adding a bajillion parameters. And you're taking advantage of the structure of your input data. That's sort of the key. So you're no longer just blindly saying, I'll apply a deep neural network. You're doing something smart at least. You're saying, all right, this is an image. Pixels that are next to each other tend to define certain things in the image, so those are going to matter, and I should do something with those together. And I should do something with only those. Because if you had a super deep neural net, you could probably do that anyway. It might pick up on that. So I think that is all we're going to have for tonight. And we'll close off on the 3-wolf moon. The 3 images of 3-wolf moon, all howling at the moon. And we'll be back next week. I might do more Theano. I might try more of this convolutional neural net. We might build some of our own stuff with that. Or I might switch it up and start looking at TensorFlow's skFlow module. This is in sort of a high-level wrapper to TensorFlow, so it makes all the deep learning neural net stuff dead simple. I took a look at it a week ago. Even I was able to do it. So any of you out there would be able to quickly bang it as a hammer on whatever you're working on. All right. You guys have a good night. And I'll talk to you next week. And if you hated this or loved this, leave me a comment, let me know. And I'll try to adapt.